In the race to build truly human-like conversation with machines, we've moved beyond text. The next frontier isn't just what a model says, it's when it says it. Conversational spoken language models, or SLMs, are now designed to listen and speak at the same time, a full-duplex interaction that mimics real human dialogue. But while these systems can generate coherent responses, they often fail at the subtle, rhythmic, and precisely timed behaviors that define natural conversation. Why does this matter? Because fluency isn't just about content. It's about timing, tempo, overlapping speech, the pause before a punchline, the beat in a game of rock, paper, scissors. These aren't just quirks, they're core to how humans coordinate conversation. Yet until now, no benchmark has systematically tested whether SLMs can actually feel the rhythm of speech. That's why we created Game Time, a new benchmark to evaluate the temporal dynamics of spoken language models. Inspired by how children learn language through games, Game Time is built around two types of tasks: basic tasks, which test foundational instruction following, and advanced tasks, which layer in real-time temporal constraints like speaking fast, slow, in sync, or with silence. Let's break it down. The basic tasks are simple in concept, but surprisingly challenging in practice. Count from 1 to 10. Repeat a sentence. Recall all the vowels. Compose a sentence that includes banana in a rainy day scenario. Respond empathetically to a user's frustration. Or role-play as a pirate. These tasks seem trivial, but even state-of-the-art models struggle. Some fail to repeat accurately. Others omit keywords. A few introduce natural-sounding fillers like, "Okay, I'll start now," which, while human-like, can break a strict time constraint. Now the real test, the advanced tasks. Here, the model must not only do the task, it must do it on time. Take time fast. Count from 1 to 10 in 10 seconds. The model must not just count, it must control its rate to finish exactly when the clock hits 10. Many models either rush and stumble, or drag on and miss the deadline. Then there's time slow. Say the alphabet slowly at least 20 seconds. Again, most models fail to maintain a consistent pace. They speed up, then slow down, losing the intended rhythm. But the real challenge comes with time silence. Repeat this sentence, but wait 3 seconds before responding. This tests not just timing, but awareness of silence, the ability to pause, wait, and then speak precisely when expected. Most models either speak too soon or too late. Even more complex, tempo interval and tempo-adhere. In tempo interval, the model must speak each word with a fixed 1-second gap. In tempo-adhere, it must match the tempo of a user's spoken example, a real-time beat-tracking task. This is like dancing to a song you've never heard before, but you have to keep the rhythm. And then there's Simul-Speak, Simul-Shadow, and Simul-Cue. Simul-Shadow, repeat every word with immediate word-by-word overlap, like a mirror. Simul-Cue, respond at a specific cue, like saying scissors, when the user says shoot. These aren't just technical hurdles. They test the model's ability to listen and speak simultaneously, to perceive the user's timing, and to react in real time, the essence of full-duplex interaction. So how do current SLMs perform? We tested a range of models: Freeze-Omni, Unmute, Moshi, Gemini-Live, GPT-realtime, and a theoretical oracle called SSML-LLM, which has future knowledge and can precisely control timing via SSML markup. The results were revealing. On basic tasks, even the most advanced models like GPT-realtime perform well. But even there, some models fail basic repetition or recall. This suggests that instruction following, long thought to be mastered, is still fragile. But when we add temporal constraints, performance drops sharply. Almost all models fail time silence. They can't time a pause. They can't wait. They struggle with tempo-adhere. They can't match a user's rhythm, even when it's clearly spoken. And Simul-Speak. Nearly all models fail. They either speak too early, too late, or can't maintain overlap at all. Even GPT-realtime, a leading commercial voice agent, collapses under temporal pressure. Why? Because current architectures lack time awareness. Dual-channel models like Moshi process speech and response in parallel, but they don't coordinate timing. Time-multiplexing models like Freeze-Omni and Unmute wait for silence to speak, but they can't react during speech. They're designed for turn-taking, not full-duplex synchronization. The result? A system that can understand what you say, but not when to respond. To evaluate this, we built a dual-channel LLM as a judge framework. We transcribe both user and model speech with word-level timestamps using Whisper. Then we feed the time-aligned transcript to a large language model, Gemini 2.5 Pro, which judges whether the model followed the instruction, including timing. We validated this method with human evaluations. The correlation between LLM and human judgment is strong. Spearman's rho equals 0.677. This means the LLM judge is reliable, scalable, and aligned with human perception, especially in tasks requiring precision. And the implications are clear. Today's SLMs are not time-aware. They don't feel the rhythm of conversation. They don't anticipate cues. They don't coordinate with a user in real time. This isn't just a technical gap. It's a fundamental limitation in building truly fluent, natural, human-like dialogue systems. Game Time isn't just a benchmark. It's a wake-up call. It shows that fluency isn't just about words. It's about timing, tempo, overlap, silence, the beat, And until we build models that can feel time, not just process it, we'll never achieve the kind of conversation that feels truly alive. Our hope is that game time will inspire a new generation of research toward SLMs that don't just speak, but synchronize. That don't just respond, but dance with the user in real time. Because in conversation, timing isn't just a detail. It's the soul,